Kimi 3 scales information across sequence, depth, and width. Most people first notice Kimi 3 for its size and its long context. The more useful story is how information moves inside the model. I'm Mehrdad. In this lesson, we'll walk through the architecture described in the Kimi 3 technical report. Text enters as token embeddings. Images and video pass through MoonVit v2 and a lightweight projector, which maps their visual features into the same embedding space. From there, the network scales information flow on 3 axes. Along the sequence, hybrid attention mixes tokens for long context. Along depth, attention residuals let layers retrieve earlier representations selectively. Along width, a stable latent mixture of experts performs sparse channel mixing. Those 3 mechanisms meet in a 93-layer network and produce the next token output scores. If this is useful, like the video and subscribe for more model architecture lessons. Start with the sequence axis. Kimi 3 does not use the same attention recipe in every layer. It repeats a 3-to-1 pattern, 3 Kimi Delta Attention layers, or KDA layers, followed by 1 gated multi-head latent attention layer. Within each KDA layer, a fixed-size recurrent state replaces a sequence-growing key-value cache. A channel-wise retention factor first controls what remains from the previous state. A delta rule update then writes the current key and value information. This gives the recurrent path a direct way to represent order and recency. Every 4th attention layer switches to gated multi-head latent attention, or MLA. It compresses each token's key-value representation into a lower-dimensional latent vector, then reconstructs the keys and values used for global token-to-token matching. The MLA layers use no positional encoding. Sequence order still enters through the surrounding KDA recurrence. The final network layer is also gated MLA. Most layers therefore carry history in a fixed state, while periodic MLA layers reopen global matching. Now look at depth. In a standard residual network, each layer receives 1 running state that compresses everything computed before it. Attention residuals treat depth more like a sequence. The current layer can selectively retrieve earlier representations, including the original embedding, instead of accumulating every earlier output uniformly. The method applies root mean square normalization to the keys. So large magnitude layer outputs do not dominate the look-back weights. Full attention over every earlier layer would keep too many representations alive in memory. Kimi 3 therefore uses block attention residuals. Layers are grouped into blocks, each block is reduced to a summary, and attention runs over those block-level representations. The embedding remains available as a source. Layers can now look back selectively without retaining a full all-to-all residual graph at every step. Along with, much of the model's capacity sits in its expert layers. Each attention layer is followed by a stable latent mixture of experts. 2 shared experts process the full hidden width. The routed path first projects each token into a smaller latent space, runs the selected experts, normalizes their aggregate, and then projects it back to the model width. For each token, the router activates 16 of 896 routed experts. This extreme sparsity creates 2 practical risks. Internal activations can grow unstable, and routing load can collapse onto a small subset of experts. Kimi 3 addresses them with 3 mechanisms. Root mean square normalization controls the routed aggregate before the up projection. Sigmoid tanh unit, GLU, soft caps both multiplicative branches to limit activation outliers. Quantile balancing derives each expert's routing bias from score margin quantiles, targeting the desired load without an auxiliary balancing loss or a sensitive fixed update step. Shared experts keep common transformations full width, while specialists remain efficient in the latent path. Architecture is only half the story. Kimi 3 then follows a 3-stage post-training pipeline. Supervised fine-tuning builds a cold start agent policy from synthesized trajectories that pass multi-stage verification and human review. Those trajectories use extensible token markup language, or XTML, to represent reasoning, responses, and tool calls consistently. Quantization-aware training also begins here, using MXFP4 expert weights with MXFP8 activations. Reinforcement learning then trains specialists across 3 domains: general tasks, general agents, and coding agents. Each domain is trained at low, high, and max reasoning effort, producing 9 expert teachers. Partial rollout prevents slow, long-horizon trajectories from stalling every update. Per-problem token budgets shape reasoning effort, while an agentic generative reward model evaluates non-verifiable general tasks. Finally, multi-teacher on-policy distillation, or MOPD, consolidates those teachers into one unified policy. Deployment remains part of training through quantized experts and a draft model for speculative decoding. Where do those post-training tasks come from? Not from a flat random prompt pool. The report describes a knowledge graph-guided synthesis pipeline. Agents start from core seed domains and expand a directed concept graph through web search, reusing nodes to limit duplication. Edges always run from coarser ideas to finer ones, until a concept is atomic enough to stop. At synthesis time, the system samples related nodes, pulls ancestor context into a keyword set, and retrieves real public materials, papers, posts, and code. A synthesis agent then chooses a task type, coding, knowledge, vision, and more, and builds a training instance from those materials. So the graph does not just store facts, it steers coverage, what domains appear, how fine-grained the concepts are, and which real artifacts become agent tasks. That is the Kimi 3 architecture path: sequence, depth, width, then post-training. If you want the next model architecture lesson, subscribe and turn on notifications. Thanks for watching.